Hello everybody, my name is Rolando Chacon. We are in the School of Civil Engineering of UPC here in Barcelona, and this video is aimed at providing some ideas about the resistance of cross sections. We have discussed already a lot of topics related to cross sections, but in the particular case of this video, the focus is on local buckling. We have discussed the definition of classification of cross sections. We have discussed the resistance of sections, I-shaped, hollow sections, circular sections, and so on, under tension, compression, bending moment, shear force, and the corresponding interactions. In this case, local buckling, we will present a definition of the phenomenon together with a mathematical and physical background for then going deeper into the effective width method, which is the basis of Eurocode 3 when it comes to local buckling. Finally, we will present exercise number 9, which is already uploaded in the learning management system. Okay, local buckling. Local buckling is a phenomenon that occurs in compressed panels of some cross sections, or compressed panels that are class 4 of a particular cross section. In this plot, we have 4 pictures. Let's focus on the right top one, which is an element in which we have some applied load that generates negative bending moment. That is to say that compression flange is on the bottom, whereas in the right bottom part of the slide we have an element which is subjected to bending, in this case positive, and the compression flange is on the top. The compressed flanges for both cases that were initially straight are no longer straight. They are not flat. They are wavy. They have some different shape now due to the compression load or component that comes from the moment. If we go to the left part of the slide, especially the bottom left part, we have a tube, a rectangular or a square hollow section, which was tested in the laboratory. This test was controlled, and in this case the tube was subjected to pure compression. And we see in this case that the initially flat surfaces also are wavy. Okay? There are waves in all sides actually of this tube. Let's focus on an idealized picture of this phenomenon, which is the top left part. We have a rectangular hollow section or a box girder, or we have a plate girder, which is also an ice section subjected to bending. Okay, so it means that there is a flange which is compressed, there is a web which is partly compressed and partly under tension, and this is a typical phenomenon. So here we have that the compression, or we define that the compressed flanges or webs are wavy, okay, just for idealizing this situation. When does that happen? That's a very important question. This happens when the stress applied on this element exceeds a certain value, okay, and this value is called the elastic critical stress. This formula will be a little bit complex now. We haven't discussed global backplane, and this is the first time instability appears in these sessions of steel structures in the way we have organized. And so this formula is a stress. This is the unit of this formula is megapascals. We can see that because there is a unit of megapascals in the elasticity modulus E, and then all other magnitudes like pi, 12, Poisson, and then we have that there is here a geometrical relationship between the thickness of the plate and the width of the plate, and so the units will cancel, and then we have a factor which is k sigma. Okay? This is the solution, that the mathematical solution that describes the point or the amount of load, necessary amount of load for generating this phenomenon of instability. It means that when the plate is subjected to this sigma stress here, when this sigma equals the value that is shown on the top part of the slide, then it buckles, then it becomes wavy. Okay, but normally this stress is smaller than Fy. Okay, this is the definition for class 4. Remember the plot of class 4 in which we cannot achieve the yield stress. It doesn't happen. So it's smaller, and we want to know to which extent, which is the ultimate capacity of these elements, because this is not the Fy. And for that, we will go into the physical phenomenon that has been studied in recent, not recent, but in the last century, is that what happens in the stress distribution of such plate when buckling occurs, is that the initially uniform stress, I will put the line here and a line here, which shows that this was initially uniform. At the moment of buckling, in which there is a wave, the stress migrates somehow from the center to the border. Okay, this is an idealized situation, and this is what one can observe if this is done in under controlled conditions in the lab. And the idealization is that it happens that somehow we could, or we can assume that the final distribution of this stress is that there is some stress in the borders and there is no stress in the middle. All stress have migrated from the center to the borders. Okay. The mathematical solution of this equation depends on the boundary conditions and the types of stresses that are applied. Okay, so this solution was, this case corresponds to compression only at one site, in which all borders are simply supported. SS means simply supported. But if we had some other parts of the plate that are fully fixed, then the boundary conditions of such differential equation will change. So that's why we have a K which is different from this case or another. Okay, in this case we also have simply supported, but one of the borders is free. And well, we can have several combinations, not only from the perspective of the boundary condition, but also from the perspective of the stress applied. Here you can see that the plate may be subjected to pure shear with different boundary conditions, or pure bending with different boundary conditions. So it means that we more or less know the elastic critical backlink stress, sigma CR, I will call this sigma CR, which depends on the boundary conditions, depends on the type of stresses, depends on the elasticity modulus, the Poisson's ratio, and more, or very importantly, it depends on the thickness of the plate and the width of the plate. The width, B, we'll just put this B here. This width is the width on which the stress is applied. Okay, so this is a little bit of mathematical description of the solution. It's not the description of the procedure, how to get there, but only the solution that is already presented here. Okay, so with that, what we are saying is that any element that is subjected to, let's say, bending or compression in a theory of bending, okay, regular theory of bending, in which we know that the strain plane epsilon, which is related to the how the sections, the plane sections remain plane after deformation. That we know, but in the case of stresses, what we are saying is that after buckling, the stress goes from the center to the border, a certain value, or the border, not the whole border, but a border whose width we will define. This definition is something that we will just call BF, which means effective width. What we are saying is that the width, which is effective, the width on which the stresses are being applied, is a little bit smaller than the total width. The total width B and the effective width BF. Okay, that's a definition. Now, that's the method, effective width method. So it means that if we have an element like this that has originally a gross cross-section and a neutral axis which is symmetrical, we could define another element in which the stresses will be applied only in the effective width. They will not be applied on what we call the non-effective part in orange here. So this section is the section which is capable of resisting our bending moments or our actual forces. This is the resisting area only. And the resisting area only in this particular case, this particular example here, means that we have something like a channel, a U-section with two borders on the top. If we calculate the geometrical properties of this new section, which is a fictitious section, this is not real, this is only a way of understanding how it works. So this section would have less area, and the centroid of this section, the neutral axis, would shift from the original position, which is the gross cross section, to the fictitious position that helps us to calculate the resistance. So we have some kind of difference here. Okay, so the idea would be to calculate a reduced section, an effective width of the originally cross section, and with the new one we can calculate the resistance in the same way, or as assuming that this new element is class 3 and we can calculate it exactly as it was previously with an elastic modulus, and we can calculate the sigma and Fy exactly in the same way we calculate previous cases. We will see that afterwards anyways. So it is necessary to define two things. We need to define where and how big is this effective width. How is this reduction systematically established by the guidelines? That's a very important question, because it depends on the types of stresses, it depends on the boundary conditions, and it depends on how this element is loaded somehow, and what's the original size, what's the original configuration of it. We have here 3 examples. This example number 1 is a channel section. This channel section seems to be subjected to purely axial force. It means that this purely axial force, or this cross section, which is channel 1, we have a neutral axis. Okay, that's good. But we know that this is class 4. It may be class 4 in the web and the flanges, or only in the web. In this case, all panels seem to be class 4. So the reduction of those panels is, we reduce in the middle panel, this is ineffective. This is ineffective here, and this is ineffective here. So we say that this does not exist. This is only a fictitious saying, I insist. And then the only thing we obtain now is the white parts. The white parts which have another neutral axis. There is a shift in the neutral axis, but also they have less area, they have less second moment of area, and they have less elasticity or elastic modulus. Okay, this is a fictitious new section which is weaker than the original one. In the right part, we have 2 examples of an effective width of a section that was subjected to bending. Okay, in this case we have a nice section, classical, and we see that here we have a reduction. This is a non-effective part, whereas in the top flange of the box section we have a reduction here. So you can start wondering, okay, how or where we need to define those ineffective areas or non-effective areas. They seem to be randomly sparse, but this is not random at all. This is depends on a very structural consideration we will see afterwards. Okay, so with that, what is the way of solving this and to rationalize it? Okay, this concept of effective width, which is assuming that the stress will be applied only at a couple of parts of the plate, which is simply supported in this example, and because this stress comes from the initially regular distribution to the final distribution of stresses in the borders. So the key of the solution here is let's define or create a final stress here. I would call this sigma CRF, okay? And this final stress will be equal to the yield stress of the material. Okay, we will equal this, and because we will assume that at the borders the stress will achieve Fy. Only at the borders, not in the middle, because in the middle it doesn't work, it's buckling. So the same equation we already had for the case of elastic buckling the critical elastic stress previously defined, we will put, instead of putting B, the total width, we will put BF. Okay. We put BF here, okay, all this formula. It's similar shape than previous one. In this case, rearranging a little bit this equation, if we multiply this equation by B squared and we divide this equation by B squared, it means that we are just multiplying the equation by 1. And what we can do is to take out BF from this equation and put B in the equation as well. So in this way we can separate terms and we can say that this equation becomes the elastic critical buckling stress that we have from previous experience, okay, in which we use total B, and then we have B squared on the top because we multiplied it by B squared here, and then we have BF squared on the bottom, and this equals Fy, so no changes. Okay, so rearranging this equation, we have that we have the elastic critical buckling stress on the bottom, we have Fy, and then we have this magnitude, which is B over Bf. Well, if we invert this equation, this is a little bit more interesting to plot this equation, which is inverted. We have it here. Look at this. So you can see here in this parameter that we now define as rho, this is the proportion between what is the border and what is the total of the width. So now new parameter appears, which is lambda. This lambda, what is this lambda? This lambda is called the slenderness of the plate, okay? And if we define Bf over B as rho, the initial equation provided by the one who created this method, which is von Karman, this equation is rho equals 1 over lambda P. Okay? Notice that there is a bar on this lambda. So this is an hyperbola which is plotted in green here. This green one is the von Karman expression. So this von Karman expression is a simple hyperbola in which rho equals 1 over lambda P. Okay? So this is a mathematical derivation. This is a mathematical way of understanding the problem. So this lambda P is depending on the elastic critical buckling stress and the yield stress of the material. It's an hyperbola, and the maximum value it may yield is 1 because rho, not lambda, sorry, rho the the solution of this equation, the maximum one is 1, because the proportion between the effective width and the total width cannot be greater than 1. Okay, so in this case, it means that the plate buckles for when the yield stress is happening in the plate precisely. Okay, so we have this von Karman expression that was modified by another researcher called Winter, and there was a modification aimed at including the effect of the residual stresses and imperfection in plates. Plates are not perfect when we calculate these things, so we needed to add to the expression a little bit of more complex initial conditions. So the initial differential equation became a little bit more complex, but at the end something happened that the researcher obtained a more realistic expression called the Winter formula, in which rho equals a quotient between lambda p minus 0.22 and lambda p squared. Okay, and then we have this Winter formula, which is under the von Karman, and that relates rho and lambda. There is another one here, which is Euler. Euler is a reference here only. We will discuss the Euler curve in point number 8. Okay, next video, or not next video, a couple of videos more, but we will discuss it further. Okay, which is for not for local backlinks but for global backlinks. Okay, so what we need to do now is to calculate rho. Calculate rho as a function of lambda for all plates, for all panels, for all walls of a particular section. And for the determination of this value of rho, we need to take into account the type of loading, the boundary condition, and the material. With this, we can calculate rho, we can calculate then a new element whose area is smaller than the total area, whose second moment of area is smaller than the full second moment of area, and whose elastic modulus is smaller than the cross-section elastic modulus. So we will calculate 3 magnitudes now. Or first of all, we need to calculate one magnitude rho. With that, we can calculate a new magnitude AF, another IF, and another WF. With this basis, in Iroko 3, the definition of rho is presented in this way. The reduction factor rho was then adapted to cases of that it was adapted statistically and was improved from the Winter and von Karman expressions. And now what we know, or what we have in Unicode, is an expression which is different for internal compression parts and for parts with free edges. Okay, we have two types of rho. Notice that these elements are in the first part. We have that rho is a function of lambda and a new element called psi, and whereas in second expression for parts with free edges, the expression is only dependent on lambda. So what is lambda? Lambda p with a bar equals the square root of Fy over the elastic critical backplane stress. And since we know which is this elastic critical backlink stress, theoretical one, which is dependent on the boundary conditions, V over T, and Fy, and Poisson, and elasticity modulus, and all this, we can just rearrange all these magnitudes or multiply and put values into the initial numbers and get into this final um, simplified form, which is B with a bar over T over 28.4 epsilon and the square root of K sigma. So there are two things here that are critical or that are important to understand, that are K sigma and also C, which is the ratio between deformation at the extremities. Let's see tables for that. And K sigma is obtained from those tables, which is the corresponding part of local buckling factor as a function of the relationship between deformations and, well, boundary conditions and all this that comes from mathematical solution of the differential equation. So we need to define rho. Rho seems to be easy, but we need to define rho in a proper way by introducing the right value of K sigma and the right value of C. Both comes from the analysis of the structure. Those elements are key. Another key element is to define the ideal critical stress for local buckling, which is sigma CR, but this formula was given previously here. And notice that in this case we define another one which is called the sigma E here. And sigma CR can be also decomposed into sigma E times K sigma. So we don't have the formula coupled with sigma, but we can separate it. This is handy sometimes to separate it because then we can look for K sigma in other ways, and sigma E will be very easy to calculate because there is no tables involved. It's only geometry and material, and pretty straightforward way. But K sigma, we just split it out from this expression. So let's go to these tables that we now find in your code. These tables provide information for K sigma, and these tables provide information for C as well. We have two different tables. We have table in which we have reduction factor for internal parts, and we have tables for obtaining reduction factor for parts with a free edge. So what's internal part and free edge? So let's have a look at it with an example. The example is this particular case. This is a particular case in which you can understand how to use the table. We have here a box girder or a square hole section, depending on the size on the nature of the production of this element. And we know that this top flange is compressed. We can understand that this top flange is compressed and this top flange is very long compared to the width. So we have a width of the flange which is A, and we have a length of this flange which is alpha times A, and alpha expectedly is much higher than 1. Okay, I'm sorry for that. It's much higher than 1. Okay, so here we need to know what's the value of sigma, K sigma. K sigma is here in the table. And then with that, we need to know how to obtain rho. Rho is here. Rho is somewhere. We have rho, we have sigma, and we have the way of putting rho or putting the effective area in the section. The question is, if this is a class 4 panel, how big is the effective width and where is that effective width? Okay, so the how big is calculated with a formula. Rho is here, either this or this. We are now in an example that defines a flange, but this flange is internal somehow. It is supported by webs, two webs, and expectedly on the edges of this beam we have some type of support. Let's say it is welded to a column on one side and it's perhaps welded to a column on the other side. So it is supported, the flange will be eventually supported by one web, another web, one column, another column. So it's fully supported, or it's simply supported on all four sides. So this is actually the table we need to use for those cases. A plate which is simply supported at all sides, and it's fully compressed on one side. So with that information we can start presenting one thing. First one is psi. What is psi? Psi is the relationship between the deformation of a section, one border, and the deformation of the plate at the other border. So if this element is, if this element is compressed, the deformation of this element at one side and the other is identical. So here we have that they define deformation at the borders as epsilon 2, epsilon 1. Let's say this is 2 and this is 1. So both are identical. So the ratio between epsilon 2 and epsilon 1 equals 1. Okay, because since they are compressed symmetrically, they will be exactly the same. So we need now, or we have now, that psi equals 1, and we can read from the table that since we have alpha greater than 1 as well here, so we have that the value of k sigma is 4. So we have 4, that's definition. It is, of course, it comes from a mathematical solution, but we don't know the mathematical solution here. You just use the mathematical solution. And so we are in this case, in which the plate goes, the stress of the plate migrates from the center to the borders, and BFF can be calculated as rho over total B, and we know that the proportion of the effective width, which is shaded in this plot, is half goes to one side and half to the other side. So it's the most simple case, the simplest case in this analysis. So what with the value of 4, we go back, we calculate, we put 4 here, We know the value of epsilon, we know the value of t, the value of b, 28.4, and we can calculate lambda, and with lambda we go to the internal compression part formula. We can calculate rho, and then we can calculate, since we know c already, it's 1 in this case, uh, so we can calculate everything, and that's it. Let's go to another case. Let's go to the case in which we have a flange from an I section. So this flange is a little bit different because I will try to put here another color. This one. No, this is not a good idea because it's a little bit, I don't know why. Maybe again. Yes. We have one border, another border, and another border here. 3 borders of this case, which is compressed as well. But in this case, we have 3 borders that are for sure supported. One long border, which is the web to flange junction. Then 2 small borders at the end that should be welded to some column or some other beam. And then we have a free border here, which is, or which should not be welded to anything. So we now have something here that appears, which is free edge. What we have here is that this corresponds to the long border. Sorry, I don't know why this becomes so big. But what I'm saying is that this is alpha A, this side, long side, and then we have 2 smaller sides. Those smaller sides are the sides on which the stress is applied, and then we have a very long free edge on one of the parts. So this table is different from the other. That's the main difference. In this solution we have a free edge. So if we go here to search for the K sigma here, we have another value different from the previous one. We have 0.43. That goes to the formula to calculate rho and or to calculate lambda and then rho, and in this case very important to point out that we will use the formula for parts with a free edge. So here, right? A lot of red marks in this case, in this slide. First example, internal part for flanges and webs, and second example, internal part for flanges and webs with a free edge. So let's go back here because I didn't define the web actually. We can also define this part. What is happening with the web? Main difference between the web and the flange here is not the nature. The web is also supported at 4 edges, so the web is similar from the geometrical perspective to this table, but the difference is the stress distribution, because here we will have epsilon 2 and here we will have epsilon 1. So now epsilon 2 over epsilon 1, this is the flange, I would put here flange, and for the web what we get is minus 1. Okay, those are opposite in sign, so with minus 1 we will get a value of k sigma much higher, which is 23.9. So with 23.9, and we know that psi equals -1, we will go to the formula, and in this case for internal compression part, and we will get lambda, we will get psi that we already know, we will get rho, and then we go back to the case in which we put this rho in a particular area. That will be a little bit different because now we are in this case. This case is for the flange, and this case is for the web, because psi is -1. So the table helps us to define not only rho, but the location of the non-effective area. Okay, so that's the mechanics, and that's the vast majority of examples we will do will have this shape, because we will discuss in this course especially elements subjected to bending and compression, no more than that, simple cases. So with that, we can start wondering questions such as, let's determine the effective width in the following cases. Assuming some values of H, W, TW, BF, and TF, you can start wondering how to calculate or determine the effective width in the following cases. Let's say an I-shaped section subjected to axial force, a I-shaped section subjected to bending moment about the major axis, bending moment about minor axis. In this case, a T-section subjected to a moment about major axis, both cases major, but in one case positive and in the other case negative. So I think this is a very good exercise to start. And I would say that with this case we can think about preparing some questions for if you don't understand how to calculate it. Okay, so thanks for listening this video. Let's work a little bit on that. This is a very important topic in steel structures, local buckling. So yeah, thank you again.